So next up is rates of change in rational functions. Example 1. The graph of the rational function f of x equals x over x plus 3 is given here below. Determine the average rate of change of the function over the interval -4 to -6. So here's -4, here is -6, and all we're looking for is the slope of this secant line, or the average rate of change. Notice I've messed up this interval here. It should be from -6 to -4, because x has to be less than -4, bigger than -6. So we're looking for the change in f of x divided by the change in x, which would be f of -4 minus f of -6 over -4 minus -6. If we determine f at -6, that's equal to -6 over -6 plus 3, and that gives us +2. And f of -4, that would be -4 over -4 plus 3, and that gives us +4. Sub these values into our quotient, and we have 4 minus 2 over -4 minus -6, so that's -4 plus 6. So that gives us 2 over 2, which gives us an average rate of change of 1. So this is the slope of the secant from -6 to -4. Next, let's estimate the slope of the tangent at the point where x equals -5. So we're looking for the instantaneous rate of change, or the slope of the tangent line at x equals -5. So first we'll set up our intervals. And with our intervals, we can now determine our delta x. And now that we have our delta x, we can determine our delta f of x. So for our first one, we have f of -5 minus f of -5.1. And using your calculator, you should end up with decimal 0.71429. For the next one, it's f of -5 minus f of -5.01. And I end up with decimal 0.74627. And for the next one, I end up with decimal 0.0074963. Finally, let's determine delta f of x over delta x. And for our first one, we end up with decimal 71429. The second one, decimal 74627. And with the third one, we end up with 0.74963. This looks like it's approaching 0.75. I'm not yet confident, so I can take a fourth interval, so let's do that. And I can see clearly that's heading towards decimal 0.75. So this tells us that the slope of the tangent at x equals -5 is approximately 0.75. So what we found here is that for this graph, if we go to -5, we just determined the slope for this tangent line. And we saw from the average rate of change we had a slope of 1. So the slope of the tangent clearly should be less than 1, and 0.75 is less than 1. Part C. Why can there be no tangent line where x equals -3? We'll hopefully see at x equals -3, the function is undefined. There's a vertical asymptote there. And since the function is undefined, we can't have the slope of the tangent, nor could we determine the slope of a secant if it included the x value of -3. Example 2. The graph of the rational function 20x over x squared plus 4 has been given the name Newton's serpentine. At which point is the slope of the tangent greatest? And then we're going to estimate the slope of the tangent at this point. So if we're looking for a tangent line, you see there's negative, negative, negative. There appears to be 0 there. When are we going to get the greatest one? Well, if I look here at 0, it looks like we're going to have the steepest slope no matter where we draw a tangent line. So based upon the graph, the point in which the slope is greatest will be at x equals 0. So how do we estimate the slope of this tangent? Well, we just do our interval tables like we've done previously. So let's set up our intervals. From there, we can determine our delta x values. Next up is our delta f of x values. So we want f of 0.1 minus f at 0. And when I determined that value, I ended up with decimal 4988. For our next interval, I ended up with decimal 0.4999, rounded 9. And for our final interval, I determined the value to be decimal 0.0499999. Taking delta f of x and dividing by delta x, I ended up with 4.99, then 4.9999, and then again 4.99999 and 9. And hopefully you can see that clearly the instantaneous rate of change, or the slope of the tangent, is approaching the value of 5. So using the same graph, at which point is there a local maximum? And then verify. So from our graph, we can pick out that at the point 2, 5, we have a local maximum. And notice, at that point, if we were to determine the slope of the tangent, we should get a slope equal to 0. So that's how we're going to prove or verify that this is a local max. Let's determine that the slope at x equals 2 is equal to 0. All right, so let's prove it. So first up are the intervals we are going to use. And again, determine your delta x values. Our delta f of x values, so in this case we want f of 2.1 minus f at 2. And I ended up with 0.00595. For the next one, I ended up with 0.0000622, and for the third interval, decimal 0.0000625. Now if we take the delta f of x and divide it by the delta x, for our first one we'll end up with decimal 0.595, then decimal 0.00622, and then finally decimal 0.00625. And you can see we're getting closer and closer to 0. And now we have shown that the slope of the tangent at x equals 2 is approximately 0, and this verifies that at x equals 2 there is a local maximum.